Okay, let's get started. So in the previous class, we were looking at how the MOS device behaves. We concluded yesterday's class by looking at what is the uh, how are the capacitances in a MOS device behaving.
Sir, you are on mute, sir.
Oh, oh, I'm sorry, man. Yeah. Now can you guys hear me?
Yes, sir.
Yeah,
Yes, sir.
probably. Okay, okay. Yeah,
Yes.
thanks, thanks. Yeah. All right. So in yesterday's class, we kind of concluded our discussion on MOS behavior. We looked at some of the layouts. We looked at how it looks actually appears in the layout view. And also we looked at the capacitors in a MOS device. Okay. Today what I'm going to do is, let me start sharing my screen. So I'm going to kind of primarily start, show you things from layout and other things. But let me start off with this. So today we are going to look at resistors and capacitors in CMOS PDKs. Okay. And as we start off with this, I want to, maybe first show you, this is how the stack up actually looks. Okay. When I say stack up, this is, let me just zoom out. Right. So this is how your CMOS IC, a typical CMOS IC stack up would look. When we say stack up, this region here at the bottom is basically your substrate. Okay, so you can see that there is one transistor here and there's another transistor here and so on. All right. Now in yesterday's class we saw that how you make a contact with the poly to the lowest metal layer. In this case it is the metal 1 layer here. Okay, and as I mentioned in yesterday's class, this particular version that I'm showing has got 8 metal layers. So this is, maybe I'll just zoom in. Yeah. So you have metal 1, metal 2, metal 3, 4, 5, 6, 7 and 8. Okay. Now for each process, what is the thickness of the metal layer? What is the conductivity of it, and all those things will vary from process to process, from technology to technology, foundry to foundry. Okay. But each of them will have a certain amount of thickness, and it is surrounded by dielectric metals. So only where you draw the metal layers you'll have the metal, otherwise you'll have these other lightly colored dielectric materials being present. So in this region here, there is no, this is just a representative figure, this is not the layer of anything actually. So if there is no metal routing, you'll only have dielectric. Okay, but if there is metal routing, in the place of the dielectric you'll have the metal. So this is how your stack up looks like. And in yesterday's class I showed you how you can route in metal 2 or route in metal 1. So like that you can use the other devices also. Now the reason why I showed you this is to kind of show you how are resistors made and how are uh, capacitors made in a CMOS process. All right. So first let's
Sir,
start off. Yeah.
sir, here you're always showing like how to contact metal 1 with the transistor. Like how do you contact metal 2 with the transistor, sir?
Sorry, you contact metal to transistor. What was the other question?
Met
Metal to?
how do you metal to second layer, sir? Second layer
Yeah.
of metal, how do you contact that to transistor? Make a
Okay, so
contact
you
there,
have to
sir.
go via the metal one only. Okay, so if I zoom in and see, you have this V1, right? So V1 is what is called as via. Yesterday I explained about vias and I showed you in layout also, right? So if you want to connect this metal 1, metal 2 to, let's say, this transistor or anything here, you have to go down using via, go to 1 and then make a contact. All right. So
Okay, sir.
even if you are in metal 6, you've got to literally come down all the way to metal 1 and then use one of these contacts to make contact with the thing. All right.
Okay, sir.
Okay. And you can see all these layers have different names, and in this next slide they have, next page they have given all these different, their thickness in terms of micron. You can see that these are all very very thin layers, right? And each of them have their own dielectric constant. Okay. And finally happens is, when you come to the top, this is what is called as the passivation layer. Okay. So when you are connecting it using bond wires, like, so when you, if you look at any IC, for example, you all would have used op amps or used different digital ICs having this DIP package, right? Dual in package, DIP packages, right? So what happens is, How do you make contact from the chip to the outside world? Basically what you do is you kind of, they will form an opening in the passivation and they will make a contact to this metal 8 layer. Okay, so all the contacts to the outside world, they will have what is called as a bond pad, and there will be a bond wire connecting here to the outside, uh, to basically the pin on your package, the IC package. Okay, so that is how you connect to the outside world. Okay. Now, let's go to how do you form resistors. Now, there are different types of resistors that are offered in different processes. Now, I have taken the example of a 65 nanometer CMOS process offered by a foundry called as UMC, based out of Taiwan. Now, UMC is one of the more popular, a very large, semiconductor manufacturing company, which is a commercial fab. Okay. Now, this is from their particular PDK, which we use for our research purposes to design circuits. Now, there are different types of resistors. Let me see if where, yeah. Okay. Now, in this particular process, they offer different types such as, non-salicide, some, P plus or N plus poly and diffusion resistors. So that is to say, you can have, you can use the poly material. Okay, if you remember polycrystalline silicon is the material which is used for the gate. So you have the oxide layer, which is an insulator, and on top of that, some of the more modern processes use metal gate, but in this 65 nanometer process, they use a polycrystalline silicon as a gate. So that material can be used because it will have a certain resistivity. You can use it as a resistor. Diffusion is also another very good resistor. What is diffusion? You can have N plus diffusion or P plus diffusion, the same material that you use to create the source and the drain regions, right? They have a certain resistivity. All right. So you can create a bar of the diffusion or bar of poly, and then you can use. So they offer what is called as non-salicide and salicide. I really don't know what it is, but these different offerings. So anyway, we don't go deep into how they do these things and so on. But these are all the things that are available. Okay. Now there is also a special material given, which is high resistance material, which gives you a higher resistivity. All right. So depending on the value of resistance that you need, you will go ahead and go and pick up one of these things. Okay. Now, rather than showing this here, let me move over to a layout. Okay. So I just took the example of a few resistors. Now you can see that the dimension of all the resistors is same. Okay, the dimension of all the resistors is, I think, 2 micron by some 0.25 micron or something like that. Okay, now let it show. So the dimensions are the same for all the 4 resistors that I have shown. Okay. So the if you see the dimension, the segment width is 2 micrometer and the length is 10 micrometer. So that is the same for all the 4 resistors. Now this first resistor is with that special high resistance material, and the resistance of this particular thing is 5.1K. Okay. Whereas this is a N-type diffusion. I have used ND. So it is the N diffusion which you use for your NMOS devices, and the resistance for this bar of diffusion is basically only 484 ohms. If you use poly, you get 1.16K. If you use P-type diffusion, you get 651 ohms. Okay, and you can see that if you use a P-type diffusion, you are putting it inside a N well. So you can see that there is a N
Sure.
well here. Of course, for even the other. Yeah, someone
Hello.
had a question? Yeah.
Yes. So actually, these resistors are basically the NMOS or PMOS transistors only,
No,
that
these are
we are
not
using,
transistors.
or these are the
These are not
special.
transistors actually. These are just resistors. Okay. These resistors are built out of the materials, the same kind of material that you use for your transistor. You understood? Yeah, this is not a
Okay,
transistor,
sir.
this is just a resistor.
Okay.
So you can think of it like, so for example, this is poly. Of you use poly for resistors, but then here, you have used poly in transistors, but here what you do is you just use only the poly material. There is no diffusion on either sides. So it is not a transistor. You just use that poly material to realize a resistor. Okay. And based on its resistivity, its resistance for this piece of poly happens to be 1.16K. Of course, this is a special material for resistor, but whereas these two are diffusion. This is the diffusion that you use for NMOS transistor. Of course, you don't have a poly here, so it is not a transistor. You just make use of that N plus diffusion itself to create a resistor. Otherwise, how will you have resistors on chip, right? How do you create resistance? So these are the ways by which you create resistances, all right? And these are non-salicided resistances. There is also salicided, N diffusion, poly diffusion, and p-type diffusion. Those will have lower values. Okay, so if you want a really high value of resistor, obviously you go for this HR material. If you want some very low resistance, like in the order of hundreds of ohms, you use these N-type diffusion or P-type diffusion. There is also the salicided N diffusion and salicided P diffusion, which I have not shown, where the values will be even, for a dimension like this, it will be even less than 100 ohms, some 70 ohm, 50 ohm, something like that. Okay. And if you want very low values, like let's say 1 ohm, 2 ohm, 0.5 ohm, that kind of resistance, you use the metal resistors. That is, you take the existing metal layers that are there and you just use them as resistors. Okay. So this is how you cover the whole range of resistances that you need. Of course, needless to say, if you want a 1 mega ohm resistance, then the area occupied by your resistor will be very large, right? You can put multiple segments like this in series, or you can put like this in parallel and realize whatever resistance you want. But typically, as your resistance value goes up, the area occupied by the resistor simply blows up. So here the area occupied is 2 micron by 10 micron. 10 micron is the height here, and the width here is 2 micron. Okay. Now, when you talk about these resistors, let me just zoom into this portion. See, up to this point is the actual resistor material. Now, this resistor material is also literally at the bottom of the chip, right? You need to make contact with your metal layers so that you can use it for all your connections, because at the end of the day your resistor has to get connected. Now for that, what happens is, here they have extended, they have put multiple contacts here. You can see all these squares here. So it is like what, 3, 6, 9, so 10 by 2, 20 contacts have been put here, right? So these contacts make contact with this metal 1 layer, that is that wiggly line that you see here, right? And let me show you metal 1 layer. So this is your metal 1, all right, and you make the contacts to the metal 1. So for every resistor you have some extension area, right? Your actual material ends here, right? But then for every resistor you have that little extension area where you put the contacts and you make contact with your metal 1 layer. So the total resistance, if you see in this thing, this is how they give the total resistance. Okay, so we will go through all these terms, but if you look at this R naught is 2 times R end. R end is those extension areas that you have at the end of the resistors, and the actual resistance is given by this sheet resistance formula. Okay, so what is sheet resistance? I don't know how many of you are familiar with the concept of sheet resistance. Yeah,
So,
someone had a question.
so can we use transistors as a resistor, so purely as a
Yeah,
resistor?
as we saw, I think couple of classes back, in order to use a MOS transistor as a resistor, it should be in the deep triode region, right? So even if when you have AC signal,
Otherwise, not
yeah, then
possible.
it is possible you will have a voltage controlled resistor, but the catch there is your VDS has to be very, very small. Okay, for example, the VDS has to be less than, say, 20 millivolt or less than 50 millivolt or something like that. All right, so let's say you are having an AC signal which you are trying to amplify. Then what happens is you are restricted, even your AC signal swing has to be restricted to that level only, right? If you have, let's say, a 200 millivolt peak to peak signal, then obviously your resistor changes like anything. You have a heavily non-linear resistor, right? So which is why you cannot use the MOS transistor as a very good resistor. It acts as a resistor over a very small subset of voltages. Okay. So yeah.
Sir, can you open that layout once?
Yeah.
Sir, here the blue color
I
part is
think
what?
this is poly.
Is it a
There is a HR material. I think that kind of connects to poly. There are so many layers here, so you have to kind of go through it and then see what it is. So up to this is that HR material. I think this is poly. I think they both might kind of, be interconnectable. That's what I'm thinking.
okay? And
Whereas for the other things,
okay,
yeah,
and the
for the other
extension
things,
is
the extension is diffusion only. Okay, so this is an N-type diffusion. It is directly diffusion, which is extended. Okay, maybe let me. Yeah, so you can't distinguish. It's fully diffusion. All right.
okay, sir. So then that
So
R edge is only from the polysilicon contribution from the polysilicon, sir. That formula which you showed.
Okay, so for each of them it will be different. For example, if you take the diffusion resistance, right, you have a certain W by L, right? You have a certain width and length for this device, right? So that width and length kind of stops here. Okay, when you say 10 micrometer, let me just use a ruler to show you. Your 10 micrometer is this much only, all right? Now, in order to make contact, you have this little extra, let's say, how much extension do you have? Like it's around, no, around 1 micrometer or 0.8 micrometer, or let's say 0.7 or so extension, right? So in this case, it is a diffusion extension, and in this case, it's a poly extension. In this case also, it's a diffusion extension, all right? So depending on which type of resistor you're looking at, that extended area is what is called R end, or rather the resistance due to that extended area. Does it make sense? Yeah.
Okay, sir.
Yeah.
Yes, sir.
So are the resistance size is greater than the size of transistor here?
See, transistor also you can make whatever size you want. All right. So in this case, in yesterday's class, I showed you a 2 micrometer by 60 nanometer device. So it's a very small transistor. And yes, you are right in the sense that this is a 10 micron by 2 micron. So this is definitely bigger than your transistor. Okay. But at the same time, you can
Okay.
have big transistors. Okay. You can have transistors whose width go up to 50 micron, 100 micron, and so on. Okay. So you're not restricted in that way. Of course, there is an upper limit, but that is quite high. All right. In fact, those who took the RFIC class will remember that I mentioned for power amplifier design, you will use the dimensions which are like, 1000 micron width, or 800 micron width, or even 1200, 1600 micron width, and so on. That is for power amplifiers and so on. Okay, so that is possible. What you will do is you will each small transistor, you'll have a smaller transistor, but you'll use multipliers. Okay, so that's how you do. But yes, in this case, comparing to the example that I showed you yesterday, the resistors are larger. Okay. All right.
Okay,
Yeah.
sir.
So let us talk about sheet resistance. So I'm not sure how many of you are familiar with the concept of sheet resistance. Right. So when you talk about the resistance of any material, you have the resistivity given by rho, and then into the length divided by the area, right? So this is width into thickness. So let's say we are considering a bar of metal or any material, right? So it has a certain length in this dimension, width in this dimension, and thickness in this dimension. Okay, and rho is the resistivity. Okay, now what happens is sheet resistance is defined as rho by T. Okay, now the reason that we define this quantity called as sheet resistance is because you cannot, these two parameters you don't have any control over. Okay, so when you are working with a certain process, okay, the thickness of the metal layer is set by the foundry. You cannot go and change it. Okay, that is set in stone. All right. Same way, the resistivity of the metal layer also, it is given. You cannot change that. It is usually resistivity of copper. Okay, copper metal is used for all the different metal layers. Okay, so these two parameters are fixed for any given technology node for each metal layer. So for example, what will happen is in this 65 nanometer technology node, the metal 1 thickness is smaller, and metal 2 to metal 3, metal 4, metal 5, metal 6 have the same thickness, and metal 7 has a larger thickness, and metal 8 has a really large thickness. This is the way that the foundry has given for this particular technology node. All right, or this flavor of the technology node that is offered to academic institutions for tape outs. All right, different other offerings may be there where the sizes of the metal layers and other things will be different. Okay, so all these details are there in the documents that are given by the foundry. So you will see that the sheet resistance of this will be greater than the sheet resistance of these metals, which will be greater than the sheet resistance in this particular area, in this particular order. Okay, the rho anyway, because it's all copper material, it will be remaining the same. So now when you talk about the actual resistance, you talk about the sheet resist multiplied by the quantity L by W. Okay, so this is how you uh, do, because L and W are in your control. Okay, you can decide how wide you want the metal to be and how long you want the metal to be. In the example that I had given, I had taken the length to be 10 micrometer and the width to be 2 micrometer, and as a designer you have complete control over these two parameters. All right. Okay, now this quantity L by W, okay, it kind of sounds a little similar to your W by L ratio of your transistors. Here it is the other way around. Okay, it also ends up being counting as being squares. All right, so this is, if you take, let's say, the top view, um, the layout view, this is your W, this is your L. Okay, now in the case that we had where this is 2 micron and this is 10 micrometer, you can draw 5 squares here, right? 1 2 3 4 5. My drawing is bad, but you know if you can kind of picture this, so you can have a 2 micron by 2 micron squares. Like that you can draw 5 squares, correct? So therefore the total resistance is 5 times the sheet resistance. Okay, so this is a very quick way by which a lot of people, especially in the industry, they will calculate the resistance. They say how many number of squares are there. Okay, so this also means that if you widen your device, if you increase your W and you keep the same length, obviously you'll have lesser resistance, right? So let's say I'm taking my W to be, let's say, 5 micrometer, and this is still 10 micrometer, you have only 2 times the sheet resistance. All right, of course this also comes from the L by W ratio. All right, so don't get kind of confused when you see some textbooks or some papers or some people talking about the number of squares. So they'll just count the number of squares in your resistor, multiply it by the sheet resistance, and that gives you the resistor. All right, so coming back to our that data sheet that was given here. So you can see that 2 times Rn plus, this is the Rs into L by W plus delta W. So of course they have, some little more other things, the delta W and other things they have calculated. Basically this is some resistor width bias at 25 degrees centimeter, 25 degrees Celsius and so on. Now this is your basic resistance. Now this resistance will also have both temperature coefficient as well as voltage coefficient. Okay, so if you take a diffusion resistor, it is diffusion in a certain well, so there is some diode sitting there, right? Now that diode will have some kind of a voltage coefficient. Okay, so that is modeled by these terms. Okay, this is your voltage coefficient, linear voltage coefficient, and the quadratic voltage coefficient. Same way, you have a temperature coefficient. So this models your behavior of the resistor with respect to temperature. So like that, they have given the equations for different resistors. I just want to show you, how they have, okay. So this is the model accuracy. Yeah, voltage dependence. Okay, so this is some sinusoidal resistor. You can see that this one has a very minimal kind of dependence on voltage. Okay, now voltage coefficients are given here, and here you can see that the diffusion resistor has got a little more variation in terms of voltage. Okay, so there are resistors which have more variation with respect to voltage and some which are more constant across voltage. All right, so you can see that this has even more spread and so on. Okay, and whereas this is the HR voltage coefficient and so on. This is with the temperature. Okay, so you can see that the N plus diffusion resistor has got a larger temperature coefficient, right? And each of the resistors, so some of them are having positive temperature coefficient. You can see that the resistance increases with temperature, right? For polyresistor, the temperature coefficient is negative. It decreases with temperature, right? So certain things are positive, certain things are negative. So depending on whichever process you are working with, you have to see how the temperature dependence is going to be. All right. So any doubts, any questions about resistors? All right. Now we'll move to capacitor. Yeah.
Sir, once. No, sir, it's
Right.
fine.
Okay.
Sorry.
Now we'll move to capacitors. Now how to form capacitors on chip? Now the motivation for putting capacitors, resistors, all these things on chip is, if you don't put them, for every connection of resistor or capacitor, you have to kind of pin out those connections, right? So if you want to connect a capacitor, you have to have two pins on your chip just to connect the capacitor, another two pins just to connect the resistor. Of course, that's a waste of pins, and also it increases your bill of materials, right? When you talk about designing a product, if you have everything integrated on a single chip, then it is much cheaper. Otherwise, you have to buy resistors, you have to buy capacitors, and so on. Okay. Of course, there are some large values of capacitors for which you have to go off-chip capacitors, put off-chip capacitors, but there are a lot of on-chip capacitors that can be used. Okay. Now, this is one type of a capacitor which is called as a MIM capacitor. Okay. The reason it is called as a MIM capacitor, it's because it is a metal insulator metal capacitor. Now MIM capacitors are not offered on all different processes, but in this technology node it is offered. Okay, the way it is done is that this MIM capacitor sits between two metal layers. Okay, this copper metal is in this technology node, this is metal 7 and this is metal 6. Okay, so between metal 7 and metal 6 you have this capacitor arrangement. Okay, so where you have a MIM top metal, you have a special high K dielectric material, and then you have a MIM bottom metal. Alright. So if you, what happens is you have a top plate, a bottom plate, and a dielectric. It's a very straightforward, two plate capacitor. And the connections are made as shown here. The top plate is connected through a VR to the metal 7 layer actually here, and the bottom plate is also connected through a VR to the metal 7 layer. This is what is called as a MIM cap. Now, as you can expect, this capacitor will be fairly linear. Why? Because it's just two metal layers and a dielectric in between. Okay. Now, but the other thing is that obviously the capacitor density that you would get, that is the capacitance per unit area, is quite less. Okay. In this technology node, I think it is something around 2 femtofarad per square micron. That is, if you have a 1 micrometer cross 1 micrometer MIM capacitor, The capacitance offered here is only 2 femtofarad. All right. So typically capacitors on chip are quite low in value. You cannot have microfarad range capacitance or even nanofarad range capacitance. Maximum you can go up to few picofarads of capacitance. All right. So capacitors will actually take up a lot of area. When you look at the overall area of an analog IC, a large amount of area will be taken by capacitors and resistors. In RFICs, inductors are the big area hogs. Okay. This shows the breakdown voltage. So up to some 7 volts or 6 volts, it is fine. 7, 8 volts, it is fine. And yeah, scrolling down. So again, this also has a certain voltage coefficient, but you will see that the variation with voltage is very small. Delta C by C in term percentage, it's all 0.03B04 percentage. Okay, it's quite linear. Okay, although the curve is kind of shown like this, if you look at the x-axis values, it's a very linear capacitance and it's across a very large bias value. Okay, so this is a bottom plate and other things. All right, and you also have a voltage temperature coefficient. You can see this is the temperature coefficient. Again, it is the delta C by C is very minimal. It's not very large. All right. Now, one thing that you must understand is that when you talk about a capacitor, there are also some parasitic elements. What do we mean by parasitic elements? There are some unwanted elements which come along with the capacitor. Okay, you expect only this capacitance, but what are the unwanted elements that you get? You have some resistance in this via, some resistance in this metal routing, some resistance in the top and bottom metal, right, and in this via and other things. So you have some parasitic resistance coming in series with your capacitance. All right. Now on top of that, if you look at the structure, I said this is metal 7, this is metal 6. If you go way down, you'll basically have the substrate, right? Now all these things will have a substrate tap also. Now this bottom metal plate also makes a capacitance with your substrate. Okay. In other words, if I were to draw and show you, it is like this. You have some capacitance here, and let's say this is your substrate, and let's say you are going to have, usually you'll put substrate tabs and so on, right? So there is a parasitic capacitance between this and the bottom plate. So the actual capacitance is going to look something like this. You have the main capacitance C, or let's call it the C naught. You will also have some resistance here, some resistance here. But between this and ground, which is your P substrate, you have your parasitic capacitance. These are the two terminals of your, let's say this is terminal A, terminal B. You have some R series resistance on both sides, and you have a parasitic capacitance from the bottom plate. So this is what is called as the bottom plate. From there to the substrate you have some capacitance. Of course, C parasitic will be much lower than C naught, but still you will see in some of the applications this actually plays a role. Okay, this is something that you should know. Okay, any device that you take, in addition to what you have, you also get a little bit of junk added to it, and this is the junk added for your MIM capacitor. Okay, the same way if you look at resistors, right, this resistor is basically sitting inside, this is basically sitting inside your substrate, right, P sub or N well something. So for example, if you take a diffusion resistor, right, this diffusion resistor and this P sub is going to form some diode, right, and this diode is going to have some capacitance. Now all these resistors will also have a third terminal which is basically a substrate contact. All right, this will be a substrate terminal. All right, so what will you have? Along with your resistor, you also have a little bit of distributed capacitance with your substrate. Okay. So that is what you basically get. Okay. Now these are all the parasitic that are there, and you should be aware of these things when you are doing your design. All right. Now let's look at one more type. Yeah.
So can we use MOS capacitor?
Yes, we can use MOS capacitor. I'll come to that. I'll talk about MOS capacitors also. I'll try to complete that in today's class. All right. The answer is yes, you can.
Okay, sir.
All right. Now there is one more type of capacitor that is used, okay, which is called as a MOM capacitor, which is a metal oxide metal capacitor. Okay. Now its structure, the top level structure or the layout structure looks like this. Okay. It is basically two interdigitated structures. So maybe I can show you. So it is like you have multiple fingers. All right. So you have, let's say, one plate of the capacitor having these fingers and another plate having fingers like this, and they are going to be interdigitated like this. All right. So you can see here that these are the fingers, the light blue ones are the fingers for port 1, right? This is one plate of the capacitor. The dark blue ones are the fingers of the other plate. All right. So what is happening is these are all metal layers. So from metal 1 to metal 6, you can form these capacitors. So you have an interdigitated structure like this. So what will happen? Two adjacent lines are going to form capacitances with each other. And not only that, you also have this replicated one on top of each other. Okay. So you have capacitance both horizontally and vertically. Okay. So again, there are two types. One is symmetric and the other is asymmetric. The difference is basically, given here. You can see that you have multiple metal layers, right? All of them are connected together. This is the cross sectional view. So this is one finger, one port. This is the other port, two colors. In a symmetric, you basically extend it all the way from metal 1 to whichever metal layer you're using. Whereas if you use an asymmetric structure, you have a bottom metal plate in metal 1 for one of the fingers. Okay. So why do you have that? The reason is, of course, again, you have what is called as mesh type structure and other things. All right. And here you have the finger number of fingers, the length of each finger, all those things are there. Let me just show you. This also has some voltage coefficient. You can see that the voltage coefficient is very good. It's extremely linear. It's all in the order of 0.001 kind of linearity, right? And you can also look at the temperature coefficient. Okay, this is it doesn't vary too much with temperature either. All right. Now these are the advantages with the MOM capacitor and the MIM capacitor. Okay. So if I were to summarize it here, yeah.
What exactly is the maximum width allowed for filling in a particular metal layer? That will also determine the
Correct.
capacitance.
So the maximum amount of so that will be set by the DRC rules. So I think the max, so that will differ from process to process. If I remember right, I think 40 micron length is the maximum here. I think. Okay, I'm not sure. I have to check. I think L max of each finger is around 40 micron, and I think the number of fingers also will have a max number. I don't know if it's 30 or 40 or 50, something like that. Okay. So it will differ from process to process.
So in an unsymmetric fashion, whole of the bottom layer should be
Yes.
filled now. Will it be filled in such a way, or will it be following the DRC
It
rule
will
and filled?
be when you say the whole of the thing will be done, so the width will also be around some 30-40 micrometers only. Okay. So the filling is it's not a very large area.
Okay.
It will be within the DRC
Okay.
limits. Okay.
Okay.
Now for a symmetric capacitor, what happens is you have effective capacitance. Let's say C naught is our direct capacitance, and both metal 1 layers will have some parasitic cap to ground. Let's say this is parasitic capacitance. Let's say this is port A and this is port B. Okay. So it is symmetric in the sense that the parasitics are also going to be symmetric. All right. In the asymmetric case, what happens is the one layer does not have any parasitic capacitance. All right. And the other layer has a larger parasitic capacitance. All right. So the layer, whichever port has got that, bottom full metal 1 layer sheet, right? So that will have the larger, that will have the full parasitic capacitance to ground, whereas your actual capacitance is C naught and the other terminal does not do. okay, does not see this. Okay, there is a reason for doing this, because there are certain applications where you don't want the parasitic capacitance at all. Okay, and so you will, especially if you take in the context of sample and hold circuits and so on, you don't want or switched capacitor circuits, you will always drive the node which doesn't have the parasitic capacitance. All right. Otherwise, it will lead to signal errors. So I don't know if possible towards the end of this course, we might look at some sample and hold circuits where we will see that there is what is called as the charge sharing and other things are there. At that point of time, you will always drive. You always want to make sure that one node is free of this parasitic capacitance, and the other node, this is where you will actually go and drive it. Okay, so those reasons are there, which is why both things are being offered. Whereas there are also other scenarios where you want the capacitance to be extremely symmetric. For example, a differential amplifier, okay, or you are building a differential active RC filter. So you want both sides to be extremely symmetric, which is where you will go for a symmetric capacitor. All right. So this is how you,
Sir, what is A
the two
and B?
terminals of our capacitance. That's it. Right.
Okay, sir.
Yeah. Yeah.
Sir? So is the distance between two metal fixed
Yes.
in a particular node?
Cannot.
We can't change it.
At all. You can change the lateral dimensions. Okay. So for example, in this particular thing, there is a minimum distance between these two metal layers. Okay. And usually when you form a thing, that you'll usually use the minimum distance. Okay. You can make it wider if you want, in which case your capacitance will be lower, right? But otherwise you cannot bring it closer to this one. The vertical distance cannot be changed at all. All right. Now let us look at
Okay, sir.
the last one, which is basically your MOS capacitance. So as somebody asked, you can definitely use a MOS transistor as a capacitor. Okay, the way you use it is that you take your MOS transistor, you take both the source and the drain, you connect them together, and this becomes the two terminals of your capacitance. Okay, so in this case, yeah, someone's mic is on, so if you can please turn it off unless you have a question, that will be fine. Thank you. So here what happens is, you have the two terminals of the capacitor, and what are the capacitances that are coming into the picture here? We have the CGD and the CGS, right? This is your CGS, this is your CGD, and you'll also have your gate to bulk capacitance, CGB, right? Now here the drain and the bulk are all connected together, right? So CDB and CSB do not come into the picture, all right? So this is how your MOS capacitor basically is constructed. Okay, you take the MOS device, you take the gate as one terminal, you short the drain and the source together and form the other terminal. All right. Now this MOS capacitor, how does it behave? All right. So let us look at it again. Let's look at your MOS cross section. Now let us start with the negative voltage. All right. When we talk about negative voltage, it is not that we are actually setting up a negative voltage. We are only talking about the gate to source voltage being negative. In other words, the gate is at a lower potential than the source. That is what we are saying. Okay. So if you take the VGS, okay, and if you look at the behavior of the capacitance, when the VGS is negative, then what happens? This is negative. So obviously what will happen? It will attract all the holes here. Correct. Now it is kind of forming not an inversion layer, it is the same type layer because it's a P minus substrate only. But you have kind of formed a certain layer here, and therefore with this distance you get a certain amount of capacitance. Okay. Right? Because the gate is now negative with respect to the source, and of course the source, drain and the bulk or the body, all three are connected together, and therefore you attract all the holes close to the gate underside of your oxide surface. Okay. Now this is what is called as the accumulation region. What are you doing here? You are accumulating all your holes here, right? Now, as you start bringing this voltage down, that is like as you start, reducing this negative voltage, or rather increasing the VGS. So this is VGS negative. Now, beyond a point, after you come to zero, what happens? It no longer starts to attract the holes. So what happens is it starts to go down. The capacitance starts to go down, because now what happens is that these holes are no longer accumulating under the gate. They are all moving away, right? And so you have a larger kind of a distance, and therefore the capacitance drops. Okay, now the capacitance drops till a particular point, and after that what happens? You are increasing the gate to source voltage here, right? Now it is becoming positive and you're increasing it. Now what happens? The threshold voltage is now approaching. So again, now instead of the holes forming a layer here, you have the electrons coming and forming the inversion layer. So again, the capacitance, what happens to the capacitance is it starts going up and then it reaches a higher level. Okay, your threshold voltage is kind of somewhere here. All right. So you have the accumulation region, you have the weak inversion region here, and you have the strong inversion region here. All right. Now this is how your MOS capacitor behaves. And when we talk about VGS, we are talking about the voltage between the gate and the source. So the source may be at a higher potential. Both potentials will be positive, but the source is at a higher potential than the gate. Okay. Now, what does this tell us? Okay. So there is both an advantage as well as a disadvantage. Okay.
Sir, so in the accumulation region, won't it kind of form a diode structure there because of the holes in that channel?
You
P
kind of have a
plus sort
diode
of
like this, right? So
like bias.
yeah, it will
Yes, sir.
definitely kind of,
The opposite.
yeah, it will kind of form, yes. But then that is also to the same bulk, no?
And
So
sir,
this is let's say connected to the source. This is connected to terminal B. This is connected to terminal B. Even the bulk is also connected to terminal B. All of them are shorted together. So that
okay, sir.
non-linear capacitance will also come in shunt with whatever we are having. Okay. Yeah.
Okay, sir.
Now the first observation that we make is that MOS capacitance is a voltage dependent cap. All right. So which means that a good thing is that you can use it as a voltage controlled capacitance, which is what we did. Even those of you who took the RFIC course, we used this in the voltage controlled oscillator, right? By changing the control voltage, you change the tank frequency and you change the oscillation frequency. So in that way it is useful. But the disadvantage is there are a lot of situations where you want a linear capacitance, but this is a non-linear capacitance. All right. So wherever you expect linearity, so for example, let's say you are having this as in a differential amplifier. Now, as your signal swing changes, your capacitance is going to change. Now that is going to introduce all kinds of errors, right? So, but the second point is MOS capacitance density is very high. All right. So because MOS transistors are small and you get probably easily around 20 femtofarad per square meter or even more than that. Okay. So it is almost like one order of magnitude higher uh, capacitance density when compared to MIM and MOM capacitance. Okay. MIM and MOM, and also we know that MOS capacitance of course is non-linear and temperature dependence is also quite high. But whereas MIM and MOM capacitors very linear and very low dependence on temperature. But the thing is they have low cap density. Or in other words, if let's say you want to form let's say a 1 picofarad capacitance, you will end up using almost 10 times the area or even more while using a MIM capacitor or a MOM capacitor as compared to a MOS capacitor. Okay, so this has a uh, very high cap density. Okay, I've already written it here, right? Yeah, okay. All right. So depending on where you want to use the capacitance, in which scenario is linearity important to you, then you have to use a MIM or a MOM capacitance. If only the density is important, for example, there are a lot of places where you want to use a supply decoupling capacitor, a bypass capacitor between VDD and ground. So in this particular application, you can easily use a MOS capacitor because you get very good density. You can put a lot of capacitance in the same area, and you don't care about linearity here. All you need is, like, anyway VDD is VDD, right? So you don't care about linearity. Whereas if you are using some switched capacitor circuits, if you are, it is in the signal path and so on, you use MIM and MOM capacitors. All right. So with this, I'll conclude today's lecture. And are there any questions, any doubts? Okay. All right. So thanks everyone. Have a nice day. Thank you
Thank you,
guys.
sir.
Yeah.
Thank you, sir.
Thank you,
So
sir.
Thank you.
MTech students, are you guys